Hey everybody, Mr. Judson here. So we only have two types of derivatives left that we have to cover, and then I think we've done just about everything we need to do. All right. So one of them is, how do you take a derivative of a natural log? The other one is, how do you take the derivative of e raised to some exponent? We'll cover that one next week. Okay. So let's start with this. If I want to take the derivative of a natural log of u, and remember, u can represent any expression. It can be the square root of something, it can be a trig function, it can be some kind of polynomial expression. Put whatever you want in there. The derivative of that is u prime over u. That's it. That's what we're looking at for today. So if I have an expression right here, what that means is take the derivative of that, put it in the numerator, and whatever this is, put it in the denominator. And then simplify if it needs to be. All right? So let's do a quick example. Let's say I've got y equals the natural log of 2x to the fourth minus 3x. And I want to find the derivative. All right? Well, then y prime is going to equal, I'm just doing exactly what it says here. Whatever that is, this right here, put it in the denominator. 2x to the fourth minus 3x. And now in the numerator, take the derivative of that. So that'll be 8x cubed minus 3. I'm done. It's pretty easy. I like this one. All right, it's quick and easy. The one thing that we're not doing is we're not spending time proving why that's the derivative. We just don't have time to. But whenever you take the derivative of natural log, that's it. That's all you do. We're finished. I know I can factor an x out of each of these, but I cannot do that up here. So I don't think there's any simplifying that can take place. I always want to think about that, because if I can, I need to. But if there's nothing there, then that's okay. All right. Now, occasionally this will happen. You'll see d dx of the natural log of an absolute value of u. Okay. What happens if this is enclosed in an absolute value sign? Well, nothing. You do the exact same thing. So still u prime over u. The reason they do this is you can't take the natural log of a negative number. So if that expression u, if maybe it could be something negative, we put the absolute value signs there to guarantee we're doing the natural log of something positive. Okay? So yeah, if you saw that and you went, oh geez, I don't know what to do, I'm just going to do the same thing, works out. All right? All right, let's try another one. All right, so you guys go ahead and try this one. You just want to find the derivative. You almost don't even have to pause, because that's about how long it takes to do the problem. So yeah, I would take this one and say f prime of x is going to be, I'll put this in the denominator, x squared plus 6x plus 9. And then in the numerator, the derivative will be 2x plus 6. I don't think we're done this time though. I think this one can be simplified. If I factored both numerator and denominator, I could factor a 2 out of this and get x plus 3. And in the denominator, if I factor this is x plus 3 times x plus 3. So we could cancel those factors, and our actual answer is 2 over x plus 3. There's our derivative. All right, so there's actually another way to do that last problem, but before we talk about that, I want to go back and just review the properties of natural logs. And these properties also apply to common logs. So if you said log of a times b equals log of a plus log of b, same thing. Okay? This is something we would have done first semester last year in pre-calc, and we did a thorough job with it, so hopefully you guys remember this. The idea is if you're multiplying with exponents, remember we said last year, every time you see log or natural log, you have to make your head think like exponents, all right? So like x to the 5th times x to the 8th power, what do you do those exponents? You add them. Same thing here. If I'm going to multiply with exponents, I have to add those exponents, right? If I'm dividing with exponents, so that's like x to the 10th over x squared, I should subtract those. 10 minus 2 is 8. That would be my answer, x to the 8th power. So when you're dividing with exponents, you subtract those. And then probably most people remember this. If you have a log or natural log of something raised to an exponent, you can bring that exponent down in front. Okay? So I think this third rule actually could apply to that last problem. Let's take a look at it again. We're doing the derivative of x squared plus 6x plus 9. Well, what if I factor that and wrote it as x plus 3 squared? So what if I had y equals, y equals the natural log of x plus 3 squared? Well, according to our property, I can bring that exponent down in front, right? That's what we did here. We just brought the n down in front and we multiplied those. So bring the 2 down in front. So I've got y equals 2 natural log of x plus 3. And so now when I do the derivative, I've got a constant times a natural log function. So my derivative is going to be that constant times u prime over u. So y prime equals 2 times, put that in the denominator, and then take the derivative of that, which is just 1. And since as a fraction this is 2 over 1, if I multiply that I would get 2 over x plus 3. Same answer, I just got it a different way. All right? I might have to think a little harder on this one. So you know, you might look at this and go, well, I kind of like the first one because I didn't have to think as hard. And that's okay. But there will be some problems today where we have to use these properties. Well, we don't have to, but if we do, it's going to make it a little bit easier. Okay? We always like easy, right? I'll let you know when we get to that. Let's try another one. All right, so this time I've got y equals 3x squared times natural log of x squared. I'm multiplying two different expressions. That means I have to use the product rule. But while I'm doing this, I've got this natural log in here now. So when I take the derivative of that piece, I'll use u prime over u. You guys go ahead and try it. All right, so my derivative is going to be, I'll take the derivative of the first part, which is going to be 6x, times the second part, natural log of x squared, plus, leave this the way it is, so 3x squared, times the derivative of this piece. All right, so now I've got to do u prime over u. And so that's going to be 2x over x squared. And then I just have to simplify it. So I think in simplifying, our book might say you can bring this 2 down in front and then go ahead and multiply it with the 6. So we would get 12x natural log of x. That's considered a little bit simpler than the way it was written before. Here I'm going to have this x, let me do it this way. I'm going to cancel the x squared with the x squared. Okay, since we're multiplying, we can do that. And what I'm left with is 3 times 2x. So I now have plus 6x. And they may give the answer this way, or they may say you could factor a 6x out of there and get 2 natural log of x plus 1. Okay, I don't care. I look at both of those, and those are the same to me. If I'm grading a test, I could see this or this and realize instantly they're the same thing. So it doesn't even faze me. You pick whatever you like the most. We have a few of us who like to factor things, and that's okay. That's not a bad thing. All right, let's try another one. All right, so yeah, you may look at this and go, oh no, when I do u prime over u, I'm going to have to do a quotient rule in the numerator and then a fraction in the denominator. So that'd be a complex fraction. Oh, this is going to be a mess. Well, not really. We're going to make this easy. Because what I'm going to do is I'm going to go back and look at these properties that say when you have the natural log and you're dividing two things, you could rewrite that as natural log of the numerator minus natural log of the denominator. Remember, if logs are exponents, this is a negative exponent, and negative exponents go in the denominator. Just to kind of help you understand and recall some of the stuff we talked about last year. So if we write it this way, that's actually an easier way to do this problem than the way it is written right here. So I'm going to rewrite this as natural log of x squared minus 2 minus natural log of x. And remember, natural log is not a number, so you cannot distribute this to both of those. Can't do that. It's a function. We can distribute numbers and variables, but we can never distribute functions. Okay? So now what I have is a u prime over u here. I've got a u prime over u here. And we don't have to add those fractions together. All right? You guys go ahead and try it. All right, so if I'm going to do a u prime over u for this, I'm going to get 2x over x squared minus 2 minus, if I do u prime over u, I get 1 over x. Okay, x goes in the denominator, the derivative of that is 1. And I would just stop right here. I think we're good. You know, if you look in the back of the book and they have a fraction, like one single fraction, that means they got a common denominator and added those together. Multiply top and bottom here by x, multiply top and bottom here by x squared minus 2, and then see if that matches. Okay? But I'm okay with this. All right, let's try another one. All right, so let's go ahead and try this one. See if we can find the derivative. So again, one of the things I want to do is try to make this as easy as possible. If I was to rewrite this as a natural log of 3x plus 2 to the 1/2, I mean, normally that's what I would do, and I would now think chain rule, okay? But using our properties of logs, I can bring that exponent down in front, and now it's just a number, and I just made the derivative part a lot easier. Right? So I haven't done the derivative yet. All I've done is just rewrite the original function in a different way. Now we're saying that the derivative of a constant times a function is just that constant. And then here I need to do u prime over u. So times, the derivative of this would be 3, and then 3x plus 2. And so if I multiply those, I'm going to get 3 over 6x plus 4. There's my answer. All right, let's try one more. All right, so same thing. We're still trying to find the derivative. You guys see if you can do that. All right, so first of all, I see that I'm multiplying two things here. So I'm going to rewrite this as natural log of x plus natural log of the square root of x plus 1. Right? When you multiply with exponents, you add those exponents. And then I'm going to do the same thing I just did on the previous problem here. I'm going to think of that as x plus 1 to the 1/2, and I'll bring that 1/2 down in front. Now I'm ready to take the derivative. So the derivative of this is going to be u prime over u, so 1 over x. Here I've got 1/2, and I'll do u prime over u, so that's 1 over x plus 1, right? Derivative of that is 1. And then just to clean it up a little bit, I've got 1 over x plus, multiply the numerators to get 1. Denominators, I've got to distribute that 2, so I get 2x plus 2. There's my answer. And again, somebody wanted to, if you want to get a common denominator and add those together, you could do that. Sometimes I think it's good to just do that every now and then, just to make sure you don't forget how. All right? So, we learned something new, right? Remember what happens every time we learn a new way to take a derivative, we get things like, what's the slope of the tangent line? If I ask you that here, what's the slope of the tangent line when x equals 2? Well, you just plug a 2 in, see what you get. Or what's the equation of the tangent line? Now I've got to plug in a 2 back here, get some decimal number, all right, so I have a point, and then my slope, and then I'll find the equation of that. So we'll see those things come up again. What about implicit differentiation? Yeah, I went and found one of those for you too. You're welcome. You don't have to thank me. It's all right. But you do the same thing here. It's just that when I do my u prime over u, I just took the derivative of an x. That's when I write in my dx or my dy or whatever the variable is. Okay? The moment when you do the derivative in the numerator, that's where your dx and dy go. Let me get you guys a homework assignment. So this is our last piece for week 16. We're on page 321. We're going to do 43 to 55 odd, 70, and 81. All right, you guys, that's it. That's all we have. You guys have a good weekend. Mentally, make sure we're getting ourselves ready to go here because we're going to have to, we got one more thing to learn. We're going to have to start doing some review and get ready for that Central Washington final. Okay, make the push all the way to the end. Once we get to the end, we can kind of relax and go, oh, okay. All right? You guys take care. Stay safe.